Okay, because I like playing around with Mathematica, apparently, I thought it would be fun to code up this example too. So let's just take a little break and look at the code that solves this problem. Here, I've set or it doesn't really solve the problem, rather. It just plots the solution to the problem. That's two very different things. You probably could get Mathematica to solve this problem if you really wanted to. Okay, so I've defined a radius and electric field strength. Here, this is the solution that I just found to the potential everywhere outside the sphere. Okay, here I've just defined this equation, which we just talked about. It's substitute in what that Legendre polynomial is for L equals 1. And then this line here just says, hey, in this general formula, substitute in for A, the radius, which I defined up here, and for E naught, the electric field strength, which I've defined up here. Okay. In order to solve for the electric field, which is what I want to plot, I need to take the gradient of the potential. And in this case, I need to specify, tell Mathematica I want to do it in spherical coordinates. What comes out, right, is a vector electric field. This is the electric field in the R direction. This is the electric field in the theta direction. There is no dependence of the electric field in the phi direction. That's something we specified, so I get a 0 here. Okay, in order to plot this, I actually have to, I don't necessarily have to, but the way I figured it out, I wanted to get rid of this 0. Okay, so that's what this does. It just says, let's see, what did I do? Oh, let me rerun this whole thing, sorry. And that, and that. There we go, okay. So the next thing I want to do is I just wanted to get rid of that 0. So now I just have it, the electric field in polar coordinates. So that just depends on R and theta. And then this bit right here transforms those polar coordinates to Cartesian coordinates that just depend on X and Y. Okay, because that's actually what I just want to plot it in 2 dimensions. Okay, so this is a fancy Mathematica. It's just changing the coordinate system. So you get something kind of big and complicated, but it still has 2 terms. This is the electric field in the X direction. This is the electric field in the Y direction. Now I can use something called stream plot to plot the electric field lines. And all it really needs is a vector electric field in order to do that, or a vector field. It doesn't have to be electric field, but some vector field, which I've defined here, the lengths of the vectors at different points in space. Okay, so I plugged that in, and then I gave it the range that I want it to plot over. So from X equals -10 to 10, Y equals -10 to 10. And then this bit just puts a disk at the middle, which represents the actual body itself, because this particular solution is not accurate. If I could get rid of this red dot, and I would still have an electric field plotted below it, but because of the boundary conditions defined the region outside of the sphere, this solution is not the right solution inside the sphere. So I put the red dot over it for that reason. Okay, but you can also think of this as the conducting sphere that we put in the electric field. Anyways, it's pretty cool. So based on what we just solved and a little bit of extra math and some tricks to get it to plot nice, we actually do get to see what the electric field looks like near what a electric field looks like when you put a conducting sphere inside that constant electric field. Again, I think this is a pretty cool example of what we're learning about. And you can play around with this again if you'd like.